let's start with a very simple crystal. Let's look at atomic chain. I would even I can also call it monoatomic chain. Okay, so it's a chain of atoms and it goes on forever. Okay, so let's say this distance is A. Okay, and it continues like that. So what do we know about this? We know that the wave function of this object is composed of two parts, right? One part was a plane wave, e to the ikx, and the other part was u of x, that is periodic. So this one is periodic, meaning that u of x plus a is u of x. So far, do you have any question? No? So what does this mean? It means that if I happen to have some sort of a wave over here that is psi, okay, over here it's, let me call it phi. Over here it's phi times e to the ika. Would you agree with this? Because you have shifted, there's a repeating part and there's a plane wave on top of it. So this atom would have around it e to the I2ka or e to the ik times 2a, whatever, right? What do we have here? We have phi times e to the minus ika, phi times e to the minus ik2a. So far, do you have any questions? So as I mentioned earlier, it's actually simpler to solve infinite atoms, infinite number of atoms versus two atoms. Okay? In two atoms, you had a 2 by 2 matrix. Do you remember that matrix? We had this on-site energy. Okay, we got this matrix from 2 by 2. Do you remember this? Yes? So two atoms, 2 by 2 matrix. But here, we actually have one atom. That's why I called it monoatomic chain. It's just one atom that keeps repeating. Okay? Let's focus on that atom and see what that atom sees. What that atom sees is its wave function is phi, or you can call it orbital, whatever you call it, okay? I'm a bit less rigorous today, even less than I'm usually in terms of rigor. Do you see? It has two neighbors. It's connected to two neighbors. Of course, we are assuming that only nearest neighbors are interacting. So I just have this one atom, so my matrix is going to be 1 by 1. 1 by 1 matrix. Okay? And these are just images of 1. Like this is 1 prime, this is 1 double prime. Are you following? Yes? So let's talk about self-energy, not self-energy, on-site energy. Let's say the on-site energy is E0, and I write it at the 1 by 1 part, because there's only one box. Whatever I get, I will write it here. Okay? But then when it comes to T, if you remember, there was T involved, right? When it comes to T, and minus T, in terms of these overlaps. It's actually modified. Before, we would just write minus t, but this time we are going to write minus t times e to the ika in this direction and minus t times e to the minus ika in this direction. Now, why we need to do this? Because let's go really back to the definition of t. Do you see the definition of t over here? Yes? It's an overlap integral, right? So if your overlap integral phi star Hamiltonian prime phi is equal to minus t, okay, there's dv here. Now, if one of them has a phase added to it, a phase, right? Then you are going to have phi star h prime phi e to the minus ika. I hope you are seeing the difference here. So that's why it's going to be t times e to the minus ika. Yes or no? Yes? So that's why we get e to the minus ika. As a result, you have minus t times e to the ika, minus t times e to the minus ika times phi is equal to energy times phi. Energy of the system. You see, the energy of the system becomes k dependent. Also, the solutions become k dependent. So you have something like this: E0 minus t e to the ika e to the minus ika. Do you see it? Tell me. Where? Okay. Yes, thank you very much. Do you have any questions at this point? So since it's 1 by 1 matrix, we can just take this one equal to that one. Then your energy depends on k, and it's basically E0 minus t times e to the ix plus e to the I minus ix is 2 cosine x, right? 2 times cosine ka. Please tell me that you are with me. Still, yes? So what does it mean? It means that if I want to plot E of k versus k, okay, this is what we call a band structure. Okay, let me put it in the middle. This is what people call band structure. And as you can see, we start from E0 minus 2t. Do you agree? Because at k equals to 0, it is E0 minus 2t. And it starts as a negative cosine, goes up, comes back down, and keeps repeating. And this energy is E0 plus 2t. Okay? And you can see that there are interesting stuff going on here. For example, after this point, the energies keep repeating. So all the information that you need is actually already present within this pi over a minus pi over a cell. Okay? So this is what we call reciprocal space. Reciprocal space. So real space is the space of x, y, and z. Okay, reciprocal space is like Fourier transform of x, y, z, and it is kx, ky, kz. In our case, we have one dimensions, it's just k. Okay. Now, what does this plot tells you? So when you have one atom, you had, let's say, one energy. And we were talking about single orbital, right? We would bring together two atoms. Each one would bring one orbital per atom, let's say, and they would split and they would make bonding and anti-bonding orbitals, right? Now here we have infinite number of atoms. All of them are bringing in one orbital, okay? How many energies are you expecting? How many energy states are you expecting? Infinite, right? And you get what you expect. There are infinitely many energy states here. Do you see? Because it's a line. All these are possible solutions to our problem. Okay, I'm tired of putting dots, but all those are separate solutions. Since you have infinite atoms, you have infinitely many. So basically what happened is that every atom contributed a level, an energy level, okay? And when you have infinite number of them, that creates one band, okay? One band, and we see that band. So as you might guess, if you have two atoms each contributing one orbital, then you are going to get two bands. We are going to see that in a moment. Okay. There are other things that are very interesting here. For example, if I have phi that is written like some phi times e to the ikx, right? Or can I think for a moment? So I will not prove this, okay, but I will just give you some idea what's happening. So you are writing down phi of x as u of x e to the ikx, right? What if I add, what if I take k to k prime, which is k plus 2 pi over a? What happens then? Okay, let's write it down. So I'm writing down right now u of x times e to the I times k plus 2 pi over a times x. So far, did you follow? Now look at this. U of x times e to the I times 2 pi over ax times e to the ikx. So what just happened? This, Nothing changed. Very good. Nothing changed, exactly. Remember, this one was periodic. So u of x plus a was still u of x, right? How about this one? Isn't that also the case for that one? So let me do it this way. Let me do it this way. I'm going to write it down as u prime of x times e to the ikx. Okay, where u prime of x is ux e to the I 2 pi over ax, right? Now, if I go like this, then I get what? Help me out. 2 pi over a times x plus a. So far, did I make a mistake? What is this? Ux. And you have e to the I 2 pi over ax times e to the I times 2 pi. What is this? 1. Very good. So you can see that this is u prime of x. So u prime of x plus a is u prime x. So what is my message? My message is that you can write the same wave function can be written as a different function that keeps repeating plus k being shifted by 2 pi over a. So this simply tells you that after doing some rigorous analysis, you can say that this reciprocal space keeps repeating itself. So if you shift by 2 pi over a, you are going to get the same state. Okay? You shift from here to here, you get the same energy. You shift from here to here, you get the same energy. So all of the information about the energy, okay, is already present in the so-called first Brillouin zone. This is called first Oh, yeah. Yes. Did I make it correctly? Yes. First Brillouin zone. Okay? This is very important. Like open any random paper, you will see bands, and they are going to plot the first Brillouin zone. Okay? Good. So we have had a first peek at the bands. Now let's move to something else. Can I think for a very brief time? Yeah. Okay. Let's look at diatomic chain. Actually, it's not really a diatomic chain. It's not like boron, nitrogen, boron, nitrogen, boron, nitrogen. Let's look at the case when you have carbons, but in reality, if you take a carbon atom chain, it won't stay like this. Do you know what will happen? Oh yeah, no, of course, like it might want to make a circle, but if you keep it as a chain, it would prefer to go to, let me just, this state. Do you agree? Yes or no? So this is called cumulene. This is called polyene. And this one has a few milli-electron volts more favorable. Okay? So let's solve this one. Now in this one, there are two carbon atoms. They are seeing the same environment, right? Each carbon atom has triple bond and single bond, okay? But if you can see, they keep repeating after two atoms. Okay? So for this one, we can talk about atom number 1, atom number 2, image of atom number 1, image of atom 2, the other image of atom 2, atom 1, and the other image of atom 2. Do you have any questions at this point? Are you lost? Okay, let me check whether you are lost or not. How many bands do you expect to get here? 2 bands. Okay, you are not lost. Good. So this one is T1, but this one is T2. So the interactions are different. Right? Triple bond, single bond, the interactions are different. But then again, this one, you can call it phi 1, this one phi 2, but this one is going to be phi 1 e to the IKA, and this one is going to be phi 2 e to the minus IKA. So when you are going to construct your matrix, what is the size of the matrix? 2 by 2. You are following, very good. So in the 1, 1 side, you are going to write E0. 2, 2 side, you are going to write E0, but yeah, E0. Then there is 1, 2. 1 interacting with 2. What do we have here? Let's see. Let's be careful. 1 interacting with 2 has T1, and that's it. Just T1. Okay? But there is also this interaction, which is say it again.
What's the parameter T?
Very good question. Interaction. So actually they are minus T. Tell me again. Say it again.
Why you have not considered, for example, negative sign for T1 in this problem?
Yeah. It's negative. You are right. So it should be minus T1. Sorry. And the other one is minus T2 e to the minus IKA. So this one is because of this interaction, and this one, oops, and this one is because of this interaction. Is this something new for you? No, you have seen this? Where?
We had a chemistry course.
Chemistry course, okay. Then this one, looking at 2 to 1 interaction, there is also minus T1 and minus T2 e to the plus IKA, right?
Can we say that it's Hermitian, so?
Yes, it's Hermitian. Okay, so to find E, you need to actually solve this determinant, right? E0 minus E squared minus T1 plus T2 e to the IKA minus T1 plus T2 e to the plus IKA equals 0. Did you follow this one? So let me see if I have the solution. I do have the solution, and the solution looks like this. It's E0 plus or minus, there are 2 branches, 2 bands, T1 squared plus T2 squared plus 2 T1 T2 cosine Ka. Okay? So what happens here? Let me tell you what happens here. Let me first compare this one with that one. Let me just give me a moment to think, please. Okay, this is the monatomic chain. Okay, this is the monatomic chain. And it had its bands, right? And this length was A. let's draw the bands. Oops, I was hoping for an arrow. There it is. Duplicate. Let me try drawing this band one more time. Oops. Okay. This is the band of that one, and it ends over here. This is the first Brillouin zone of that chain. Right? This you have already seen. What happens is that when you introduce the other one, which was like this, right? Okay, let me just try doing it properly. So this is triple bonds, these are triple bonds, and this is single bond. I'm exaggerating a lot. Notice that the unit cell have now grown to 2A. Do you see it? Now you have something like this. So the first Brillouin zone of the diatomic chain is twice smaller. That's what you expect from a reciprocal space. When you increase in real space, it shrinks in reciprocal space, right? Now, how does this one transfer into, does this band transfer into this new world? Well, if you plot it, you will see one band forming like, can I think a little bit? Yeah. So ideally, if we didn't have this double triple bonds, okay, meaning that if T1 and T2 was equal to the earlier T, right, then it would just fold in like this. Let me tell you why. If you remember, this one was repeating, the other one was repeating every 2 pi over a, right? So if you go from here to here, it was 2 pi over a, right? Now 2 pi over a has become pi over a, okay? So it needs to repeat every pi over a, yes? So what are you going to do to get? What are you going to get? Let's say this one should repeat every pi over a. So I move it by pi over a, means that it just repeats over here, okay? And then I have another one here, right? And I move it over there. Let's say I move it over here. Oops. Has to be like this. Are you following? Or if you are good at imagining geometries, it's simply folding. It's just, you are taking just a piece of paper. Oh, I can do it here. Okay, just hang in there. Let me fold a Brillouin zone for you. Do we have a pencil? Okay, yes, it's drawing. Do you see it? Yes? So now you are folding it in. You are folding like this inside. So those things that went like this fold in like that. Okay? That's what's happening. But that's when T1 is equal to T2 and equal to T. Yes? But T1 and T2 are different now. Are you following? So,
When you said T1 and T2 equal to each other and T, you should get the above formula for energy, right?
Yeah. Let's see how it leads to the above formula. Very good point. So T1 is equal to T2.
One of them is cosine, one of them is square root of cosine.
No. Hear me out. Okay, very good point. I like it. Me like it. E0 plus minus square root. So I'm just 2t squared
Plus
2t squared
cosine
cosine
k.
ka.
Okay.
Watch the magic happen.
Small cosine.
E0 plus minus t comes out, and inside I have 2 times 1 plus cosine ka.
Okay.
Now what is 1 plus cosine ka?
Sine k.
No, not cosine 2k multiple 2
Herkes bir şey söylüyor. Okay.
Tamam geldi.
cosine 2k hocam.
Ha?
2 cosine 2k.
2 cosine squared ka over 2.
Okay.
Yes? Do you see? What do you get? E0 plus minus t. By the way, this is supposed to be 2a, because now we are in, if we are comparing two things. So this is 2a, this is 2a, so that one becomes a, right? So t times 2t cosine ka. Do you see? It's the same formula. Why plus and minus? Because now it becomes now you are unfolding the band. Okay, so you have this one and that one. You are unfolding that one. Good, very, very good. But when T1 is not equal to T2, then it starts getting away from this. Okay, this is what you expect in the perfect case. But the thing is that when you hit the Brillouin zone, notice how smoothly it hits the Brillouin zone here. Do you see? It goes through the Brillouin zone edges smoothly. That's what happens with the other one as well. So if you don't have a specific symmetry that would make it edgy, when you go through the Brillouin zone, you go smoothly. You want me to plot it? Ekin. Teaching private or shared? Shared codes? I don't think so. No. I don't have the code. Although we can write it. Should we? You want it? It will take some time. Okay, let's write it. Who wants to have the code? No one. No one wants to see the code. So let's do it then. T is of course 2.7. Bands. So what was the first formula? Two times pi to 2 times pi. E was E0 plus or minus 2 times T times cosine, this should be K, and A is 1, okay? Okay, let's make A 1, K times A. Yes? Plot K versus E. Maybe with red. Thank you. So here is the band structure. Okay. Do you see it? Good. So let's now go ahead and do the other ones. So let's say T1 is 2.3, T2 is 3.1, right? So E1 is, it's over here. The formula is E0 plus square root T1 squared plus T2 squared T2 so should we go with cosine K times 2A, right? Yes? That's E1, and E2 is the same one with minus, with negative. Yes? Tell me, you have a question? So let this be green and this be blue, E1 and E2. Okay. Yeah. Do you see it? Are you happy? There is very, very deep physics here, okay? And it's, if you understand this, I mean, it's the starting point of topological insulators, believe it or not. How? Do you see how T1 is 2.3 and T2 is 3.1, right? I just wrote it here. Yes, I can switch them and I can plot again. Do you see that it's the same thing? No, it's the same thing in bulk, but when you include edges, it's completely different. That's called SSH model. Just started talking about random stuff right now, okay? Let's go and let's Google SSH model. Schrieffer-Heeger model. As you can see, it's about carbon chains, blah, blah, blah. Description, Hamiltonian, band structure. Do you see? Now these things are familiar to you. And when you look at the finite chain solution and the edge states, one of them would have an edge state, and yeah, look. Do you see a band gap here? Yes? So if you end the chain with single bond, okay, then the edge state energy will appear right in the middle of the gap, which is going to be topological edge state. This is cutting edge research topic, okay? Topological edge state. But if you end the chain with double bonds, triple bonds, then you don't have that edge. So then the system is in topologically trivial state. Okay? Do you want to see the topological trivial and non-trivial states? What are we doing, right? You are lost. Yeah. Okay. Let me go back. It would have been fun.
Chain doesn't. How you can like say the code that chain ends in the single bond?
Yeah. Should we do it?
Yes.
Yes? Who wants it? Yes? Some people want it. So,
because the solution comes from the inherent periodicity, so
exactly. So, periodically, if you look at the bulk structure, there is a gap. But if you include the edge, there is a problem. The problem is that, let me show you what the problem is. So, okay, let's do the code, right? Let's write the code. So for the code, we need the following. There are n atoms, right? Now, we need to write a code that has n atoms, not infinite atoms, so that it boils down to 2. N atoms. So n atoms, and the first one will start with T1, the second one is T2, the third one again T1, the next one is T2, etc. Right? So if you are going to write a matrix for this one, it's E0 on the diagonals, right? And T1, T2, T1, T2, T1, T2 over here. Yes? Seems pretty simple. Just make this and then find the eigenvalues and eigenvectors. Okay? Okay. New. Save it as SSH. Clear. T1 is 2.3, T2 is 3.1. Okay.
which one corresponds to double?
The one with larger overlap, larger hopping parameter. So right now we are going to have the topologically non-trivial case because we start with single bond. I know some of you are lost completely, but it's fine. It's fine. It's not like I'm taking millions of hours from your life. It's just 10 minutes. Should be fine. M-1. Okay. Help me out here, please. N by N is E0, right? What? Ah, okay. E0 is 0. 1 to n over 2, right?
diagonal kullandım.
Yes, how do I write it?
First, let's say f diagonal as a variable.
Okay, I will not bother with that. Okay.
3 satırda bitecek, 5 satırda yazacak.
No, but I want you to also understand this code, also me to understand it. Is this the way to go? Tek sayılarla gidiyorum.
Hepsi easy olmayacak mı?
Yes. So I'm actually going to write also m plus 1s like that. Okay. And when it's odd, I'm adding minus t1.
Sadece ilk 3 diagonal non-zero değil mi?
Just watch it, okay? Okay, I am lost. n minus 1, n minus 2, t2. Okay, it's a stupid way of writing it, I know. But let's see what we are missing. So we are missing just this one and the one at the end, right? First row and the last row, are we missing only those or are we missing more? First row and the last row. So the first row should be 1 and 2 is going to be E0 minus T1, right? And the last one, so n minus 1 to n minus T2, yes? But I don't want it to end with T2. I want it to start and to end with T2. T1, sorry. Will it be the case?
And should be 29.
Is it? Oh, then it has to be odd.
Ama kodu yazdım.
Then it has to be odd. Okay. 29. I am really messing up. Let's have a break and I will fix the code.